the universe evolves and ultimately what is its fate. And I'm very happy to be here and to talk to you about the universe and what scientists now think the universe might look like on its larger scales. And that's a bit complicated topic, so in order to understand it better, it's best if we put everything into proper perspective and look at the cosmological model from the perspective of how ideas about the universe evolve. So I would like to take you on a journey through the history of cosmology and how people try to think about the universe in the past and how we try to think about it now. And that would be a quite big topic. So in order to make it short, I will make it brief, and my review will be very selective, and it also will be very subjective, and I will tell you this from the perspective of modern science, and mostly also from the perspective of European culture. So our journey begins 100 or 200,000 years ago with early humans looking at the sky. Back then, possibly, for them, stars, there was nothing special about stars. Stars were just a part of nature, like trees or clouds or animals. But then it didn't take long for them to realize that there is actually some pattern in the sky. That stars form patterns, and these patterns are constant. It's not like clouds when you look at clouds and then 1 hour later you see another pattern. Stars form patterns which are constant, except for one thing. That during the night, if you look at this during the night, you will see that everything drifts. So if you make an image, if you sit long and make an image of the position of stars, you can actually get something like this. And not only this, also there's the moon, which changes its shape and also rises at different positions along at different times of the okay, so there's the moon which looks differently at different days. So for example, one day in the afternoon you see this shape of the moon, and the moon is setting there. A few days later, moon looks like this, and 1 week later, in the evening, it doesn't set, it actually rises and it looks like this.
Where are these photos taken from? It's not from the Southern Hemisphere, it's not Sydney.
No.
Where's it from?
I'm not sure where.
Okay, so it's not here. Great, thank you.
Okay, and later on, you can see this type of a moon, but you can only see this in the morning. And after a few days, the whole cycle repeats itself. And this is a pattern that you would see here in Australia or in Southern Africa or in South Africa, because up north, where everything is upside down, people see something like this. So they see this kind of moon in the evening, and 3 weeks later they see this in the morning. And the whole cycle is very, very regular. And we don't know when, but we know that at least 30,000 years ago, people had lunar calendars. It also doesn't take long to realize that sun follows a similar pattern. So, for example, you mark a position of a sunrise at one day. Then you return to your position, then you return to the same spot a few days later or a few weeks later, and you realize that sun rises at a different position. So you make a regular observation and you see that the sunrise actually moves to one position and then returns. And it's also very regular. And not only that, imagine that you can mark the position of the sun at noon. So this is what you see in winter time, then spring, summertime, and then back to winter. There's this funny shape here. So it's very interesting and very puzzling. So you start to do regular observation of the sky, try to see whether or not you can see other strange phenomena. And then you can see that there are some objects that. Yep.
About the previous slide, that infinity sign, particular area.
Oh, this is called analemma, and you can see it everywhere. It can look differently. For example, if you were at North Pole, it would look like this.
So the shape is like an infinite sign, but
yeah.
The angle is different.
Yeah. Okay, so then you look at the sky, And then you can see that there are some objects that behave very strangely. You can see when they move, they make these loops. So for example, this is Jupiter, this is Saturn. And there are also three other objects that behave so strangely, and these are Mercury, Venus, and Mars. And the very strange thing about those objects is that they only reside in one part of the sky. When they move along the sky during the year, they only move in one part of the sky. It's not like Mars is moving here, Jupiter is moving there, and Venus is moving up there. All of them reside in the same region of the sky, and not only these, but there's also Moon and sky and Sun. They also move around this region here. So there's something special about this region, and you call this region zodiac. And maybe there's also something special about constellations in the zodiac region of the sky. So now you put everything together, and you want to construct some logical model of the universe, which will explain everything. And since everything moves around us, the simplest logical explanation is that we are in the center of the universe, and Sun, Moon, and other planets just circle around us. And then everything is just surrounded by the sphere of constant stars, which only rotates one every 24 hours. Okay, so this is the Aristotelian universe developed in the 4th century before Christ, and since then it was widely accepted, and people were developing this model. Why? Because the real geocentric model of the universe, when you apply this universe, when you take this model and try to predict the position of planets later on, you will see that this model doesn't work well. Because planets, when they move across the sky, they have these loops. And if you want to explain those loops within this model, you need to add additional circle. And then you realize that one circle is not enough. It's not sufficient. You need to add more circles. So you add a circle, you add another one, and in 16th century, you end up with a model that has something like 80 circles. So then, in 16th century, there's astronomer Nicolaus Copernicus who realized that this is a mess. 80 circles, that's a complete mess. And we can do something simpler. Let us put a sun in the center, and instead of having 80 circles, you can have a model that's much simpler. Still, Copernicus has more circles than just 8. In fact, his model has something like 30 circles, but 30 compared to 8 is something much simpler. At the time, a few people took it seriously and even take it further, like Giordano Bruno. But for most of the people, that model was just treated as a mathematical trick. It wasn't taken seriously as a real model of the universe because for people at that time, a common sense told them that Earth is in the center and Earth is in the special position, and only Earth is capable of having other bodies orbiting it. So since Earth is only body that can have other bodies circling around it, only Earth can be in the center of the universe. So a few decades later, people invent telescopes, and then Galileo points his telescope towards Jupiter. And what he sees is this. You see a Jupiter, and there are 4 stars at one side. Okay, that's interesting. 4 little stars. He returns, he leaves the telescope, he returns to his observations 4 nights later, and what he sees is this. Now, 2 of those stars are at one side, and 2 are at the other side. Now, that's puzzling. Okay, so on the 5th night, he wants to do the observation, but it's cloudy, so he returns to his observation on the 6th night, and then he sees that there are only 2 stars. Where are the other 2? Well, the obvious explanation is that they are behind the Jupiter. They are hidden behind the Jupiter. So logic dictates that there are other bodies that circle around Jupiter, and that changes everything, because now, since there are other bodies that can circle around other bodies, then that means that this model, there's nothing special about us being the center of the universe. So people slowly switch to this model of the universe. And once you have telescopes, you can also see that this strange feature on the sky is actually made of other stars. And when you look closely, you can see that those stars are not constant, they can move. Like here's an example of the Bernard stars, which moves very fast close to the sky. And the reason for that is that because this star is very close to us. So apart from the system of Alpha Centauri, the Bernard stars is the closest to us. So these are the stars in our local vicinity. And our galaxy is made of many, many other stars. And when you look at that, and when you realize that this is just a pattern of other stars, and then you see that there is a finite thickness, then the logic dictates that our universe is just a system of stars, and we are somewhere there. So that's the picture of the universe from 18th century. But the universe is not only made from stars. There are some other objects like nebulae. Some of them are very pretty, but there are also objects that are very peculiar. And those spiral nebulae, they played a very important role in the evolution of, in the way we view the universe. And at the beginning of the 20th century, there was this great debate whether spiral nebulae are part of our galaxy or maybe they are separate systems. So Shapley argues, Shapley tries to convince people that all these spiral nebulae are just a part of our galaxy, and Curtis puts arguments for those spiral nebulae to be outside our galaxy, that they are separate systems. And back then, the dispute is not settled. We have to wait a few more years for Hubble to measure the distance to the Andromeda galaxy, and then we realize that those objects are actually separate galaxies. They are separate systems. And our galaxy is just similar to those and one of millions and millions. So there are other galaxies, and the universe is full of galaxies. So now I would like to show you an animation from the Sloan survey. So this is what you could see if you were able to fly through the galaxies, through the galaxy distribution. So these are the galaxies mapped by the Sloan survey. So the universe is full of galaxies. There are roughly like 1.5 million of galaxies mapped by the Sloan survey, but in the visible universe there are millions of billions. There are hundreds of billions of galaxies.
Excuse me. How many of these have been counted for sure that there are this number of galaxies out there?
Okay, so we can do it only by surveys like this.
Right.
And this one counts like 1.5 million of galaxies. And then what you can do, you can estimate, based on your model of the universe, you can estimate how many galaxies should be up there.
But this one is for sure 1.5 million.
You just take one section and then multiply.
Yeah. You assume that what you see here should be similar up there.
Yeah. Yeah.
And so that's one of the foundation of our model, modern cosmological models, that we assume that the universe is everywhere similar. Is that the laws of physics and how the universe looks in one part should be similar to what you have in the other part.
Yeah, if you just clarified to me, what are we looking at here? Are we looking at a 3D presentation of the Sloan results?
Yep.
Of that sample of the sky?
So you map the position of the galaxies, you know where they are, and then you do the simulation.
How do you get the distance?
Based on the cosmological model. So when you have the cosmological model, you measure the position and you also measure the redshift, and the cosmological model will tell you how to convert the redshift to the distance. Okay, so that's the very good question, because if you want to know how the universe looks like, what it's made of, and how big it is, or what's the distance to those galaxies, you need to have a model, because there's nothing in the universe that will tell you the universe was made in, or expiry date, or something like that. All the interesting questions and features that you want to ask and know about the universe, you can only deduct it from the cosmological model. So cosmology, this is what cosmology does. Cosmology is a science that tries to understand the universe. And the way we do it is that we take the observational data, we then apply principles of logic and mathematics. Then we add some physical laws, and to that we also add some premises and our thoughts and the way we think the universe should look like. And based on that, we constructed a model of a universe. And then we compared it with the data. If your model is consistent with the data, that's good. If it's not consistent, then you have to throw away that model, work better, and find the better model. So, but once you have a model, you can get some extra information. Like for example here, with geocentric model, Aristotelian model of the universe. You have this model that you constructed based on the observation of the motion of planets, and now you can ask questions. Is this universe infinite or finite? And you can see that this universe is finite. It has a finite size. Is it infinite? Was there a beginning? Will be there end? Well, the way the model works is that planet just moves and moves and moves, and there's no evolution. So the logical implication is that this universe is eternal. There was no beginning, there will be no end. Now this model was then adopted by Jewish Christians and Islamic astronomers, and for them it was important for the universe to have a beginning. And also for them it was important that there will be end. So they adopted this model with one exception, that there was a creation and then there's a day of judgment, that there is also an end. So their model of the universe is not only finite within the space, but also finite within the time domain. And then comes modern science, and here, an important part of the cosmological model, of the construction of the cosmological model, is that we add laws of physics. So, in 17th century, Newton brings his theory of gravity, and when he applied his theory of gravity to the universe, he realized that since gravity is a attractive force, that you cannot have a system which is stable unless you have infinite universe. So for him, the universe, it wasn't possible to have finite size. You have to have an infinite universe. And then, in 20th century, Einstein brings his new theory of gravity. And when he applied this theory to describe the universe, he realized that the universe should either expand or collapse. And that was against what he thought the universe should look like. For Einstein, the universe should be static. So he tweaks his equations, he adds additional constant, which is called the cosmological constant, and this constant allowed him to make the universe static. So he gets a static universe, which also appears to be finite. Now that was 1917, so before the Great Debate, and that also fit nicely to the model of the single large galaxy, which was static and eternal. A few years later, after that, people discovered that there's expansion of the universe, that the universe expands. So Einstein actually throws away his cosmological constant and calls it the biggest blunder, because if he hadn't, if he stick to his intuition and to his original models, he would be able to predict the expansion of the universe. So since then, we have a model that expands. And if everything expands, that means that in the past, everything was closer and closer and closer. And also your cosmological model tells you that there was a time in the past where everything was in the single point. this point is singular, and that's the beginning of the universe. So we shift our ideas about the universe from a finite or eternal universe back to the model that has a beginning. Now, does this universe, is it finite or is it infinite? Well, within the standard cosmological models, without the cosmological constant, you have only three solutions. One is that the universe has positive curvature, like the surface of our Earth, and then in this case, the universe is finite. Not only finite in space, but it's also finite in time domain, because there is a beginning, and then eventually this model recollapses, and there is a finite time. Another solution has negative curvature, and in that case the universe is unbound, it's open, it's infinite, and there's no end. There's infinite expansion. The universe just expands forever. Now, in order to better understand what does it mean and how those universes look, how they look like, let us just hear what Carl Sagan can tell us about this. And also, it's also very interesting from the historical perspective, because back then, in the last century, the real question of cosmology was whether the universe is open or closed. What will be the future fate of the universe? If it's closed, then there will be end to the universe. If it's open, then it will expand forever.
Now, imagine a universe just like Flatline, truly two-dimensional, and entirely flat in every direction, but with one exception. Unbeknownst to the inhabitants, their two-dimensional universe is curved into a third physical dimension, maybe into a sphere, but at any rate, into something entirely outside their experience. Locally, their universe still looks flat enough, but if one of them, much smaller and flatter than me, takes a very long walk along what seems to be a straight line, he would uncover a great mystery. Suppose he marked his starting point here and set off to explore his universe. He never turns around and he never reaches an edge. He doesn't know that his apparently flat universe is actually curved into an enormous sphere. He doesn't sense that he's walking around a globe. Why should his face be curved? Because there's so much matter in this universe that it gravitationally warps space, closing it back on itself into a sphere. But our flatlander doesn't know this. After a long while, he'll find he somehow returns to his starting point. There must be a third dimension. Our flatlander couldn't imagine a third dimension, but he could sure deduce it. Now, increase all the dimensions in this story by one, and you have something like the situation which many cosmologists think may actually apply to us. We are three-dimensional creatures trapped in three dimensions. We imagine our universe to be flat in three dimensions, but maybe it's curved into a fourth. We can talk about a fourth physical dimension, but we can't experience it. No one can point to the fourth dimension. I mean, there's left, right, and there's forward, back, there's up, down, and there's some other directions simultaneously at right angles to those familiar three dimensions. Now, imagine this universe is expanding. If we blow it up like a four-dimensional balloon, what happens? An astronomer in a given galaxy thinks all the other galaxies are running away from him. The more distant the galaxy, the faster it seems to be moving. This is just what Humason and Hubble found. On the surface of this curved universe, there is no boundary or center. The universe can be both finite and unbounded. The redshift of the distant galaxies seemed to imply to Humason's contemporaries that we were at the center of an expanding universe, that our place in space was somehow privileged. But if the universe is expanding, whether or not it's curved into a fourth dimension, observers on every galaxy will see precisely the same thing. All the galaxies rushing away from them as if they had made some dreadful intergalactic social blunder. If there's enough matter to close the universe gravitationally, then it's wrapped in on itself like a sphere. If there isn't enough matter to close the cosmos, then our universe has an open shape extending forever in all directions. This saddle universe is only one of an infinite number of possible kinds of open universes. Unlike such closed universes as the sphere, open universes have in them an infinite amount of space.
So in the 20th century, the question was, is our universe closed or is it open? And so how can we measure that? The best way to measure it, one of the ways to measure it, is to measure the distance. Because if you have a closed universe with positive curvature, then the distance to a given point is always smaller than the distance to a given point in the universe that has a negative curvature. But how can we measure a distance? It's not very easy to measure distance. It's not like we can send astronauts with a big rule and to tell us how big the universe is. But the nature is very rich, and there are lots of objects in the universe, and some of them, like supernovae type 1a, can be used to measure distance. Supernovae type 1a are exploding stars, and when they explode, they mostly emit similar amount of energy. And they are very luminous. During the explosion, they are as luminous as the whole galaxy. Still, these are very rare events, and it also must be supernovae type 1a. It cannot be other type of supernovae. So it's not easy to find all those supernovae, but in 1990s there were two teams that started to measure supernovae. One was KZ supernovae team, and the other one Supernova Cosmology Project, and the leaders of those teams got the Nobel Prize last year for their discoveries. So, based on distance measurements, you can actually see which of those solutions is true. Yes?
Can I ask you one thing? You determine the distance based on the brightness. So how do you know, is it that type of supernovae that you are getting a different brightness? So how do you know if it is that supernovae or it is further?
Okay, so
farther closer.
when you observe a supernovae, you also measure its spectrum. So it's light signature, and based on this light signature, you can estimate, you can predict whether it's supernovae type 1a or some other type of supernovae.
You mean how much it is redshifted? Or?
Not redshifted, but what are the elements in the spectrum? Like, for example, does it have hydrogen or helium? If it has hydrogen or helium, it definitely is not supernovae type 1a. Because supernovae type 1a are made of exploding white dwarfs, carbon-oxygen white dwarfs. So you have to see carbon and oxygen, and there should be no hydrogen or helium. Okay, so once you have the distance, once you have distances, you can actually predict, you can measure them. It's a bit tricky because we cannot measure things into the future. We only reside here at one given time. But since light propagates at a finite speed, that means that the further the object is, we see it as it was in the past. So by observing distant objects, we can actually probe this region here into the past. And this is what was measured. So this is a similar picture that we had before. Here is size, here is time. So size and time. And 0 marks today. So here is into the future. Like here. Here's the curved universe and open universe. Here are closed universe, and this is the open universe. Now what was expected was that supernovae should be found in this orange region here, because these are the models that decelerate. So as in here, models without the cosmological constant, they always decelerate, and it was expected to see supernovae in this region here, either along those lines, or maybe this line, or this one. What was found was that supernovae reside in this blue region here, which shows that the universe, the only logical interpretation of this fact is that universe accelerates, that the expansion of the space accelerates, and that's why the distances are much larger than what you get in the decelerating universe. So from that, you definitely see that there will be no collapse. There will be eternal expansion. So what does it mean? Well, it means that the universe will expand, and eventually there will be no galaxies visible to us, because there will be only one galaxy, and all galaxies will just drift apart from us. Because if the expansion accelerates, that means that the speed at which space expands increases, and eventually one galaxy will recede from another at the speed larger than the speed of light, which means that the light will not be able to come from other galaxies, and we will not be able to see them.
Are you saying it accelerates away faster than the speed of light?
Yep. Well,
It's an interesting concept.
no, the concept of the expansion of the space is that the further a galaxy away from us, the faster it expands. And it's a natural and logical consequence of a uniform expansion of the universe. However, if the expansion is too fast, eventually there is a region where the velocity is much larger than the speed of light, and so no light, even if it propagates towards us, it just dragged away from us.
Space expands faster than the speed of light, but not that within space.
Yep.
You got it? Yeah.
This model only works on billions of years, doesn't it? Which is totally incomprehensible.
Yeah, and also depends on what drives the acceleration expansion of the universe. We don't know. We call it dark energy, but we don't know what are the properties of dark energy. The simplest cosmological model assumes that this energy is just constant. But if it's not constant, if it changes, and if it has properties of a phantom dark energy, then the acceleration will be so fast and so rapid that eventually everything will be just torn apart. The expansion of the universe will be so fast, so rapid, that it will be stronger than gravitational forces that binds us, and everything will be just torn apart.
And where will it go?
Yep.
Where will it go?
Well, that's the singularity of this model.
Sorry?
In a similar, this
I don't understand why the point of all this is done. I mean, like the saddle thing of the universe. Like, okay, so what's not universe? If this is the universe and it's got a saddle shape, what's there in the saddle? Hello.
The saddle's a two-dimensional model of a three-dimensional space, though. It's hard.
What is it where the universe is not?
That's a nonsensical question.
That's a good one.
No,
What's
it's
south
not.
of the South Pole?
Pardon?
What's south of the South Pole?
Another planet.
No, there's nothing south of the South Pole. It's a sphere. You can't go south.
Is what you're trying to sort of say, I mean, as much as my brand from Copeland is that the universe is what's got matter in it, and beyond that is no matter. So,
Well, what's that?
It's not a matter of being a vacuum, it's a matter of there being no space at all. So the question about what is there when there's no space is a question, slightly meaningless question about, what's half of zero.
Exactly.
It's a meaningless question about.
Yeah, but that's mathematics, and I'm talking physical.
Well, we're talking physics here too. I mean, I think speak would be a better example.
So you guys are saying it's not even a vacuum, it's just nothing.
Right.
It's not even nothing.
But there's no way to ask the question about it.
Yeah. So his question, I think, is in that flat model of the saddle, what's in the middle? But it's a flat model of it's a flat representation of a three-dimensional.
Exactly, that's just a representation. It's
because none of us here can think in 4 dimensions. Maybe. Carl Sagan supposedly could.
It's a very sensible question, but the problem is requiring there to be an answer that's there is a something beyond the edge. There is no edge, and so there can't be anything beyond it.
And this is about
This bit's about the observable universe, which is a different. And everything we're talking about here is stuff we can see and stuff we know is there, although we don't understand it necessarily. Well, I think the dark energy is a good example.
Well, with this big rip, that's the problem of the Kosmiczka model, because when you make your model and when you do the prediction with the big rip, you just got infinity, and it's a similar problem to what you have here at the beginning. The model also has infinity, and infinity is not a physical concept. You cannot measure infinity. It's not something physical. It's a mathematical concept. And that actually points that there might be something wrong with theory. And in order to study what happens here, you need to have a better theory that describes both gravity and quantum mechanics. And currently there are two competitive theories of quantum gravity. One is loop quantum gravity, the other one is string theory. So when you take for example, loop quantum gravity, and when you evolve the universe back to time equals 0, where there's supposed to be a singularity and Big Bang, this is what you get. You actually don't get a singularity. You don't get that matter is in one point. You actually get a bounce, because when everything is so dense and compact, the quantum forces takes over and they are repulsive.
So there's something there.
Yeah. So that means that in the loop quantum gravity there's no Big Bang. Actually there's a big bounce, and so before that the universe was collapsing, and then it was shrink to a very small size, and at that point quantum forces took over and everything started to expand again. So in loop quantum gravity there's no beginning of the universe, there's no Big Bang, there's just a big bounce. And what about string theory? Well, in the string theory there's one set of string theory which is called N theory, and in N theory you have brains. So our three-dimensional space, the universe that we see, is actually one brain. It resides in one brain. And there's always, it's not just one brain. You have to have more brains. And once you have other brains floating around this higher dimensional space, they can bounce. And when they bounce, the kinetic energy that is released and transformed to matter, this is actually your Big Bang. And in this model, you have a bounce, and then brains expand, and then at one point they come together, and then there's another bounce, another bounce, and another bounce.
These are membranes you're talking about, aren't they?
Two brains, yeah.
Membranes, yeah, rather than just brains, yeah.
And so this is a cyclic model of a universe. Well, do we really need quantum gravity? Well, actually, it turns out that for some cosmologies, you don't really need to have you don't actually need quantum gravity, because you don't really go back to this initial time when you have problems with singularities. One of the key ingredients of the standard Kosmiczka model is that in the early universe there was a rapid expansion of the space, which we call inflation. And inflation is very necessary for our understanding of the universe, because during inflation, quantum fluctuations were enhanced, and those fluctuations they are like the seeds for all the structures that we see in the universe. So, but once you introduce inflation, and once you study inflation, you actually see that if inflation occurred in one part of the universe, there's nothing wrong with inflation occurring in other part of the universe. Actually, what makes sense is that there's always a place in the universe when inflation occurs. So you end up with a model where there's only inflation, the universe inflates everywhere, and every now and then there are bubbles where inflation just dies out, and in one of those bubbles is our universe. So you end up with a multiverse, eternal multiverse, where our universe is just one bubble. So our universe in this model is finite, but it's just a part of a large, maybe infinite and eternal multiverse. So that's cosmology. Using observations and logic, and using, okay, so observations, we only get more and more data, and more accurate data. Logic doesn't really change. Laws of physics do change, because laws of physics are like cosmological models. These are not God-given. There's nothing in the universe that says that this is the law of nature and this is how it is. It's just that we study laws of physics, and in the same manner as you construct a cosmological model, you construct laws of physics, and in time the laws of physics they change. So
can I just interrupt there and say, you say the laws of physics change, but in truth what you mean is that our understanding
of nature.
Yes.
Yeah. Yeah. Laws of physics are just description of how we understand nature, and these change. And once they change, the whole picture also changes. So once you can have a model where everything is finite and eternal, then you have a model that is finite also in space, both in space and time. Then eventually we end up with a model that had at the beginning, like real beginning, that comes naturally from the model. But then when you study what was before that, it actually makes more sense that the Big Bang was not the beginning. That there was something else before that. Either it was a big bounce, or maybe it was just brains bouncing around, or maybe there's this eternally inflating universe, and our universe is just a bubble. So these are not easy questions, and currently the situation is that we have many cosmological models, and it seems that most of them are consistent with the observational data. And which one is true? And well, we hope that in future we'll be able to say which one is true or not. Well, and at the end, I'm going to also return to Carl Sagan, and let's hear what he can tell us about the origins of the universe and what was before that, and whether there was a beginning or if there was no beginning.
If the general picture, however, of a Big Bang followed by an expanding universe is correct, what happened before that? Was the universe devoid of all matter, and then the matter suddenly somehow created? How did that happen? In many cultures, the customary answer is that a god or gods created the universe out of nothing. But if we wish to pursue this question courageously, we must, of course, ask the next question. Where did God come from? If we decide that this is an unanswerable question, why not save a step and conclude that the origin of the universe is an unanswerable question? Or, if we say that God always existed, why not save a step and conclude that the universe always existed? There's no need for a creation, it was always here. These are not easy questions. Cosmology brings us face to face with the deepest mysteries, with questions that were once treated only in religion and myth.
So current understanding of observational data and our current cosmological models suggest that actually maybe the universe was always there. But
if the general
looking at the history of astronomy and the history of cosmology, everything changes. So maybe in 10, 100 or many more years, the picture of the universe will change. And let me finish this by having a look one more time at our visible universe and what we actually know from real observation, how the universe looked like. So we start from Earth, and then camera just moves back, and at every frame you will see more and more of the universe. So it's also similar to what we had in the past with our understanding of the universe. We started with Earth, and for us, sky was just part of the Earth, and then we realized that actually stars form another realm, and it's not part of this of our Earth. It's actually further. So here are satellites. There are like 15,000 satellites now orbiting Earth.
16,000?
15.
15,000, are they all functioning?
Well, no, some of them is junk.
Yeah. So that's all satellites, yeah.
And sometimes there are even collisions there.
Yeah, yeah. So how many functional satellites do you have?
I'm not sure.
No,
So we're moving further, and now we can see the orbit of our moon. Now the solar system. So that's the universe in for ancient cosmologists. So this is how you could see the sun if you were 1 light year away from the sun. Now you can see local stars. And this is the signal, electromagnetic signal. So 70 light years away from us. It was emitted in 1930s. And this is our galaxy. And all other galaxies in our local body. And then we move away and we see more and more galaxies. So these are the galaxies marked by the Sloan survey, and it's harder to observe galaxies at larger distances. It's easier to observe quasars. So these dots are quasars. And eventually, because light propagates with definite speed, the further the object is, you see it as it was in the past. So eventually, you reach the region when the universe was very young, very hot and very dense. And you cannot go beyond that region because light cannot propagate through those hot and dense regions. So we're now going back. And it's amazing that our planet is just one tiny part of this large, vast universe. And it's also amazing that we humans can ask questions like, how our universe looks like, what's the origin, what's its fate, and is it just this part of the universe, or maybe there are other universes that we live in a large multiverse? Is it eternal, or does it have a beginning? If it has beginning, what was before the beginning? So that's the questions that people ask, and that I find it amazing that eventually in the universe light was developed and you can ask such questions. And we're back on Earth.
matter which way we took off from Earth? No, I mean, what we were seeing in the images, does it matter which way we go? Is it going to be the same?
Well, it shouldn't. Well, that's how we imagine the universe. Well, the structure might be a bit different, but everywhere you should see a similar pattern. Galaxies and clusters and...
On the large scale, but on the small scale you've got the Milky Way galaxy, which is not isotropic.
Yeah, exactly. So it does matter whether you go in this direction, maybe you will pass the Andromeda galaxy. If you go in the other direction, you will pass other galaxies, but on larger scales, you should see a similar pattern.
Okay, and in 1785 there was a map of the universe. What's the 2012 one look like?
That was that one there.
Yeah.
Well, but it didn't stop.
Yeah.
It kept moving. What's the static image of the universe look like 2012? Have you got a big enough screen to show it?
Well, the image, let me just... Okay, so that's our solar system. Here are the sun, stars in our local system. Then those stars from a galaxy. Galaxies from they form groups. So this is our galaxy, this is Andromeda galaxy. Then groups from clusters, there's the Virgo clusters, and all of them, they form large superclusters. And on larger scales, this is how it looks like. Those filaments that you can see here.
Is the reference from Earth though? What's the visual reference from? So the 1785 one was someone looking up and doing a drawing.
So here, this is the computer simulation. This is how we imagine the universe looks on larger scales.
From Earth.
Yeah, if you could move, like, yeah.
Looking outside it, I think. This is actually looking outside it. From looking from outside.
I know, I find that weird. I want to know, I want a comparison to the 1785 picture. I want the same one.
No, the 1785 one was looking from outside the galaxy.
Was it really?
Yeah.
How did they do that? Jeez,
No, that was what they imagined it looked like.
Well, scientists in those days too.
They imagined. Well, yeah.
So here what you have, this is a computer simulation, which is just a box with plenty of matter. And then here, this is, you just take one slice through this universe. And this is the slice through this box.
On the image where you had, one of the images in the movie showed quasar events. What's the relationship between quasars and, say, non-observable galaxies? What percentage of galaxies would be quasars?
Okay, so quasars, this is what we see as a quasar is actually an active galactic center. And in the past, in the past, galaxies were very active. They merge. There's a big black hole inside in the center of a galaxy. Material is just piling into a black hole, and that releases enormous amount of energy. With time, galaxies just they went quiet. They're more peaceful. And so, for example, in our galaxy, there's a large black hole, but our galaxy is not active. The nucleus of our galaxy is not active. It's not like those quasars that we see. But the consensus is that in the past, you had more and more active galaxies. So when you look into a distant universe, you see a large number of quasars.
Right. So does that percentage then get very high in the far distant past with a lot
Yeah.
of
So
galaxies
in the past,
represented?
galaxies are active, and then they just get a bit quiet and more quiet.
So I saw something recently that was suggesting that the rate of star creation at the moment is expected to actually be very low.
Yes,
Is that tracking the same kind of free material to be sucked into the black hole at the center, matching up with the collapse of all the material into basically, cold planets and or suns?
Yeah, it's a bit more complicated than that, because when you have stars, you have also supernovae explosions that just eject material. So the picture is that in the young universe, when galaxies form, you have also large star formation rate. But then, due to supernovae explosions you lose the material, and then eventually you reach the point when the galaxy, the star formation rate just drops.
I think they're referring to specifically new stars with hydrogen-helium composition, as opposed to much later stage evolutionary stars with the remnants of supernovae materials. The expectation is the amount of free hydrogen and helium sort of left in the universe now is tapering off, and what they're seeing is a much lower rate of new star creation from original Big Bang source components.
Yeah, that's the cycle how stars form. You start with hydrogen and helium, and then you produce higher elements, and then so first stars, once you have just hydrogen and helium, you can form very large stars. And when you have a large star, its evolution is very rapid, and it soon ends up in a supernovae explosion. And then you have enriched material, and you can form smaller stars which live longer and longer. But the problem is that eventually with those supernovae explosions, you just eject this material, and then eventually you reach a point when there's not enough material to form new stars.
But all that discussion is about the singular cosmological model, the singularity model, with the Big Bang. All the discussions in the last 3 minutes of it has been about that. But if you were to take any of the other cosmological methods, the Dumble one, expanding and contracting, then those discussions are not
It's similar. It's the same. What we are talking now about is what happened a few billions or millions and billions after Big Bang. So star formation rate increases. Stars form a few millions after the Big Bang, and then around 5 billion years ago, the star formation just started to drop. So this is a common feature of any cosmological model, because when you form a cosmological model, you want this model to be consistent with observations. If your model doesn't have star formation rate, if it doesn't predict galaxies, then you have to take another model. So all of those cosmological models that are presented, they all have similar, they all predict the late stage.
What I'm saying, the consequences, if you have one of a different cosmological, the consequences are not catastrophic or whatever. Whereas in the model of singularity, you could conclude that the consequences are catastrophic.
Define catastrophic.
I mean, in other words, you've got to crunch. But if you've got many, as I said, in the other models where there's a continuum, well, if before the Big Bang there was another expansion, then you know that it will go on forever.
Like with the cycling universe, eventually all those brains will collide, and then everything will get closer and closer, and your universe will end, and then it will give birth to another universe. Yep.
When you talk about the universe, do you have, is there positional points? Like if I want to go from here to supernova X324, how do I go there? Do you have, like, there's no north, south, east, west, but it's...
Yeah, but direction.
Is it constant? If I head off past the moon tonight at midnight, does that get me past Mars and then I'm on the way?
Well, you know the direction because you observe the supernovae. So you go in this direction.
Yeah, but do you define that? Like, if I'm going on the planet Earth, it's north, south, east, west, and I know what the numbers are. What do I have if I'm tripping off in the spaceship and want to go out there?
He's asking about what's the coordinate system.
Yeah, coordinate system.
Well,
thank you.
Coordinate systems are invented by humans, and there are many coordinate systems, and whatever coordinate system works for you, you just implement it.
But you don't have one. You don't use one.
There are multiple
What?
ones.
Yes, we do.
Yes.
Yeah.
Yeah.
Well, tell them what it is. I think that might help. The first point of Aries and the north pole of the axis of the Earth and things like that.
Okay, so on Earth, we have north and south, right? When you look at the stars, you see that. Maybe I have another picture. So with stars, when you observe stars, you see that most of stars. Okay, this one will do. So you see that most of stars are in one region of the sky. So you construct another coordinate system where all those stars are in one plane, and this is the galactic coordinate system. You can do a similar trick with galaxies. So you observe local galaxies, and then what you see is that most of local galaxies, they reside in one plane, like here. So you introduce another system, supergalactic coordinate system, and then you can do whatever your reference, whatever your preference are. You can take any preference point, and then based on that, or any direction, based on that direction, you can construct your own coordinate system.
But all of these things are moving at the moment.
Relative.
Yeah.
True, but then once you introduce your coordinate system, and once you have it, then you can see, okay, this star is moving within this coordinate system, or this galaxy is moving like this. But your coordinate system is fixed.
Oh, I mean that all these stars, they are not moving in one direction. They are like moving in different direction. The moment that you want to define this coordinate system.
Yeah, true. So it's your choice. For example, with galaxies, you define this is my plane, here's my axis, and then you take gyroscopes, and then you position the gyroscopes to point in this direction, and that's your north, that's your supergalactic north, that's your supergalactic south, and
it doesn't matter that things are moving in a coordinate system. If you can identify where it is and say it's moving in a particular direction, it doesn't matter if it's moving, and it's fine. You can drive a car on the surface of the Earth and have a speedo. Same thing applies. It's just where do you put your coordinate system to start with, and then what's the relative motion. It doesn't matter that they are moving, as long as you can measure it and account for it.
And the point of reference is with any coordinate system, the reference points have got to be a long distance away from where you are. In other words, if you're on the Earth, you're spinning around, there's no point in having the Moon as a reference system. You have to have a far galaxy as a reference system. And that will, generally, in a short period of time, remain unchanged.
So what I'm saying is there a standard system? Is there a universal system? Universal is the wrong word here, but is there a standard system?
I would say there are many systems.
Okay, I just want to know that.
There's one that I use in my astrodynamics, and that is the North Pole, which points roughly to the North Star. Now, the star being so far away and moving so slowly, that doesn't effectively move during the lecture or during our lifetime. And then it's the first point of Aries, which is known as also the vernal equinox, is another point. Once you've got 2 points at 90 degrees, you can define a third point to be at right angles to those two directions. Then you've got your XYZ axes. So that's what we use for satellites orbiting the Earth. And you can extend those into space. Because they're an inertial set of axes, they don't rotate relative to the distant stars, so you can extend those axes into space if you want, and you could well use that for all of your astronomy if you were so inclined. That would translate very easily to where you should point your telescope on Earth, so that'd be one advantage. So that's one that I use.
Thank you.
Can you go back to your original slides that you started with? There was one slide with a chart bar of let's go back. Yeah, that one. In this slide, you're saying 33% dark energy, 23% dark matter, and less than 1% is the stuff that you see, right?
Yeah. Around 2%.
Yeah. My question is, what is the difference, first, what is the difference between dark energy and dark matter? And are these two the empty space that we do not consider to be material stuff that's made of stars and gas and dust, gas and everything?
Okay, so dark matter is like matter, and it interacts gravitationally. So it's always attracting gravitational force. And we know that there's, for example, dark matter, because when you observe the stars they orbiting a galaxy, you see that they move too fast. Well, that you cannot explain the motion if you just take into account observable matter. And it's not only that, when you have your model of the universe that expands, then you can actually, when the universe was hot and dense, you can actually calculate that what we call Big Bang nucleosynthesis. And from that, you get exactly how much matter, how much baryonic matter. So baryonic matter is the matter that we are made of, like protons, neutrons. You can get from that an almost precise number, how much baryonic matter is in the universe. But then you look at the motion of stars in the galaxy, and then the motion of galaxies in clusters, and then what you see is that there's much more matter than what your model predicts. So the normal matter that we are made of, like neutrons and protons, this baryonic matter is only 4% of total energy density of the universe. That's we know from Big Bang nucleosynthesis. From the observations of how galaxies behave, we know that there must be more matter. There must be more matter to make everything work. So the estimate is that there should be something like 27% of matter in the universe. So the rest, this dark energy that needs to be put into the model in order to explain all the other observations, it's not matter. It's not gravitationally attractive. It's actually repulsive. So it cannot be matter. It must be something else, some other substance.
Well, this raises another question. That 23% of dark matter, as you say, is interacting with the matter that we do know exists in the same way as the matter interacts, right? So it is obeying the gravitational law.
Exactly.
So if this brings up the question that how do we know that we haven't taken into account that matter? Because, for example, if you look at our solar system, we have sun, we have earth, we have moon, and all these celestial objects in our solar system. But some objects cannot be observed because they are dark, right? Because they are not as bright as sun. So how do we know that this material that is missing from our equations is really present, and we're not missing them because they are not illuminating enough light? You know what I mean? For example, we know that sun is there because it is emitting light, right? Or we know Jupiter exists because we can see it in the light of the sun. Or we know some other stuff is out there because of the magnetic fields and all those stuff. So
okay, so in a similar manner, when you look at all the stars in galaxy and gas that emits light, then you only get something like
less than
2%. 2%. From the Big Bang nucleosynthesis, from your model that fits all the observational data, the model predicts that there should be something like 4% of baryonic matter. So that means that 2% of baryonic, that half of the baryonic matter is too dark to be visible. But still, if you take all the baryonic matter into account, it's still not enough to explain the dynamics of galaxies.
So maybe then this brings up this idea that maybe our models are incorrect,
True, and there are models of modified gravity when people try to modify gravity and to have a model that is free of dark matter. Yeah, there are attempts like that, but these are not considered as standard models, and there are different issues involved with these models. But yes, you can tweak your equations. You can by hand modify your gravitational laws so that you don't have dark matter.
Gravitational lensing, though.
But the tweaking you need to have needs to make up 23% compared to 4, and that kind of tweaking at the moment doesn't seem to reasonably fit
there is evidence for dark matter as well. You can see gravitational lensing, which is where light actually bends around another galaxy.
But that doesn't
And
address whether or not
it bends too much. It bends
Yeah, but it
23% more
address
than
whether
what
it's
stars there are in a
unobservable
galaxy.
Yeah,
baryonic matter.
but the problem is that you can also have lensing in modified gravity.
Oh, can you? Okay.
It's just that it seems that the way you have to modify your gravity in order to explain lensing is a bit different than the way you have to modify your gravity in order to explain the motion of galaxies, and it's also different to the way you have to modify gravity to explain the motion of stars in the galaxy. So
it's flawed.
maybe there is some connection, but it's not the model that is widely accepted. Yep.
And the difference between dark energy and dark matter is that dark energy doesn't obey gravity.
Well, it obeys general relativity, so in that sense it obeys gravity, but it's not. Gravity is attractive force,
Right.
and in order to explain accelerated expansion, you need something that is not attractive; it's actually repulsive,
Right.
and that's dark energy. Having said that, there are models that try to connect dark energy with dark matter and dark energy. That there is some interaction between dark energy and dark matter, and that one can become the other, or the other can become one decays. That dark matter decays to dark energy, or other way around. There are models that try to connect those two, but in a standard picture, that's a very strange substance because that's repulsive. And if you, when you look at this as a point of view, when you look at dark energy as a substance, then this substance must have a negative pressure. And ordinary matter has positive pressure. Gas in this room has positive pressure. Dark energy, if you treat dark energy as a substance, must have negative pressure.
Which in this picture, it is treated as a matter, right? Because we have put it into perspective of material.
Well, this chart presents the energy density of the universe.
Okay.
And since energy can be converted to matter, so that's why you have this. So this is the content of the energy density of the universe. So 70%, roughly 70% of energy density of the universe is dark energy.
But dark energy is something which is not explained, obviously.
We don't know what it is.
Interesting.
Just there's a question on the different models in the graph there. We have the blue at one extreme and the red at the other, and a number of models in between. Do those percentages of dark energy and matter of different types, 73, 27, do those two numbers change depending on which model you choose on those two graphs?
Yes, if you tweak your pattern parameters, if you change about the amount of matter, dark matter or dark energy, you will get a different curve. So these curves represent different models with different amount of dark energy and dark matter.
Right. So the blue extreme might be 72, 28, or is it small?
Well, it can be like 80 to 10, or even
significant change.
Yeah.
On that computer modelling, when we left Earth and went out into the far reaches of the universe, I noticed that there wasn't a heaven there. I was told when I was younger, God lived in heaven, and I didn't see it. Is that true? You've come to the wrong
Well,
one.
in this model, there's if there is heaven, it's not in this model. It must be beyond that.
Heaven was in a big black Cadillac, but maybe that was just a song lyric.
Thank you.
You mentioned pressure.
Mm-hmm.
Can you tell us more about that, please?
Pressure of dark energy, or
Pressure in the universe. How on earth can it be negative, given that the pressure of a gas is always positive?
true. It depends what dark energy is. If dark energy is just because we don't know what dark energy is, there are different attempts to explain what dark energy might be. So, for example, it can be a substance, and if it is a substance, then this is a strange substance because it must have negative pressure. But it may also be that the gravity, that the way we understand gravity is wrong, that you have to modify general relativity, and when you modify that, you can get rid of dark energy. And then that means that dark energy is just a feature, just some effective term that needs to be put by hand. Just like with the geocentric model of the universe, when you had these epicycles, where you put additional circles. So that were just artificial construct put into the model. So maybe dark energy is just this artificial term that we need to put into our model. And in the more general theory, there's no dark energy, just that. But if it's a substance, then it must have negative pressure.
But negative? But you said dark energy repels.
Yep.
Or negative pressure attracts.
Not in general relativity, because in general relativity, pressure has also a weight. So when you calculate the attraction force, you take the matter density, so matter attracts, and then in your equation, matter energy density always comes with pressure. So if you have pressure, then your gravitational attraction is stronger. So for example, a dense star, because a dense star has a pressure, the gravitational attraction is much stronger in such a star because of the pressure. So that's how general relativity works. The point is that in general relativity, the gravitational attraction is connected to the curvature of the space-time. So the more matter you have, the larger the curvature. And not only that, the more pressure you have, the larger the curvature of the universe is. And that's why positive pressure actually contributes to gravitational attraction. So on larger scales, if you want to have a repulsive force, you need to have this negative. And you need to have this much bigger than the energy density of matter. So that's why you have to have more dark energy, so that this actually is negative.
Yes, right.
Well, I have another question on a different subject. We know that because of the gravity, the planets, stars, most of the celestial objects are in the shape of spheres. But to my surprise, galaxy, which has a huge amount of stuff in it, they have different shapes, and among them is the shape of our galaxy, which is in a disc shape. Why is it so? Why it's not a sphere?
Because universe is dynamic. Universe is dynamic. When you have stars, they move around. And let me see if I have some pictures of that. And not only stars move inside the galaxy, and there's also other galaxies, and you have interaction between galaxies. Okay, so here's a typical galaxy, but when you have two galaxies around, they merge. And then this all disrupts everything. Eventually, when you wait enough, when you have an isolated galaxy, when you isolate the galaxy and wait billions of years, eventually you should end up with something that looks like this, with a elliptic galaxy. But young galaxies are always spiral, and they also interact, and when galaxies interact, they get distorted.
But Milky Way galaxy, to my understanding, is not one of the youngest, it's one of the oldest, right? We are almost 12 billion years old. Why is it this? It should be elliptical, right? Or it has had one of those accidents with collisions with another galaxy.
Well, it's we are still, our galaxy is not like in a final state. There are other galaxies around us, and there's also a big galaxy of Andromeda that is moving towards us. And in 5 billion years, our galaxies will merge. And so there's lots of interaction in our local group. There's lots of interaction in our local group.
5 million years.
5 billion years.
Billions.
Isn't the shape of the galaxy a bit like the shape of the solar system? The solar system is disc shaped. So I think it's quite understandable that a galaxy is also disc shaped. No?
Yeah, the solar system is disc shaped because when it
Isn't it conservation of angular momentum?
Yep.
Yeah.
Yep. True. So you start with something that is like disc-like shape, but then if you have a large number of interaction between galaxies, that they merge, and eventually, what you end up with that you are losing some of the stars, and you end up with a core that is more or less.
So if you've got something which is flat, it's got an isotropy in its angular momentum, which means that it's flat. If you've got something which is elliptical, it means its angular momentum is relatively evenly distributed and random, which is something you'd expect it to tend to in a very long period of time. So you would reasonably expect younger gravitationally bound systems with higher enthalpy to actually have more organized structures, and over time they become more random, which is elliptical galaxies where all the exchanges of angular momentum have gone on forever and everything's evened out and there's no longer a net angular momentum, which is what would give you a disk.
So with the bounce model, is there an issue with that on over annuity? So, because you're basically not losing any energy in that model. You're not gaining any, so it's not really over annuity, but you're not losing any. Everything collapses back,
Yeah.
and then expands again, and
That's right.
you're basically left with the same amount of energy as you put in. There's no loss of energy in that system, which seems.
Yeah, but where
would you lose it to?
Yeah, well, that's a good point. But, well, to the explosions, to the heat, to the photons that are all shooting out. Like there's.
Yeah, but the whole system is closed. There's no way.
Yeah, but the photons outnumber, unless the photons collapse back in as well, and that.
Well, if you think of the metric expansion of the universe, you're talking about the metric contraction of the universe, so it doesn't matter how fast the photons go. The whole space and everything that contains all the photons ends up at that point in that model, so it doesn't matter where the photons are going, they all end up in the squash.
Yeah, fair enough.
I think you kind of have to stop looking at the universe from the outside.
Yeah.
Because you can't.
You can imagine outside.
Yeah, but you have to look at it from the inside, because that way you can actually see if it collapses, everything collapses.
Yeah, good point. Fair enough. Is that everything? Yeah.
Well, there's a question.
Oh, another one. Okay.
Yeah, my question is actually related to the string theory. Like when I read the picture of this book, like he is advocate of the he told like it explains many things, but when I read like Lawrence Strauss, he mentioned like string theory doesn't focus like not focus anything, so it's like still in a like hypothesis model. So
well, the problem is it's not only string theory. It's also loop quantum gravity, and the problem is that when you study those, when you want to study the universe on the smallest scales, there's no way we can now explore those scales with our experiments.
Yeah, but so, like most of the theory, like grand unification theory, like focus some particle, or maybe quantum gravity has some equation. Like it has some equation that it can fit and probably explain some probably unexplained phenomenon that we like couldn't explain before. But for string theory, like has it?
It depends on the version of string theory. One version is supersymmetry. One version predicts supersymmetry, and we hope to test supersymmetry soon in Large Hadron Collider. So some things are testable. There are some predictions that are testable, but in that very, very core, if you don't discover, if we don't discover supersymmetry, then superstring theory can still be correct. And the problem is that these are very fundamental things, and at our advancement of technology, it's very hard to test that.